absolute convergence and the ratio and root tests. So if we're given any series, sigma a sub n, let's consider the corresponding series, sigma n equals 1 to infinity, of the absolute value of the a sub n. And so that would be absolute a sub 1 plus absolute a sub 2 plus absolute a sub 3, etc. A series, sigma a sub n, is called absolutely convergent if the series of absolute values, sigma absolute a sub n, is convergent. Let's consider some examples. Alright, so consider the series sigma n equals 1 to infinity of negative 1 to the n over n cubed plus 6. Well, this is the a sub n, right? Negative 1 to the n over n cubed plus 6. Well then, absolute a sub n, well, basically all that happens here is the negative 1 to the nth power kind of goes away, right? Because under absolute value, any negative 1 goes to 1, and any 1 stays at 1. So absolute a sub n is 1 over n cubed plus 6. Well, 1 over n cubed plus 6 is less than 1 over n cubed, and sigma n equals 1 to infinity of 1 over n cubed converges, p series, with p greater than 1. So we know that sigma absolute a sub n converges by comparison. So therefore, we say that sigma n equals 1 to infinity of negative 1 to the n over n cubed plus 6 is absolutely convergent. All right, so we took the absolute value of the terms and we used some other test on it. In this case, we used a comparison test. We found that by comparison, the absolute a sub n converges. I should say sigma absolute a sub n converges. And so then the original series is called absolutely convergent. All right, let's consider our old friend here, sigma n equals 1 to infinity of negative 1 to the n minus 1 over n. All right, so recall that this is our a sub n, and so sigma, so then absolute a sub n would just be 1 over n. And we know that sigma n equals 1 to infinity of 1 over n diverges. All right, that's the harmonic series. But, okay, so what does that say? Since sigma n equals 1 to infinity 1 over n diverges, but sigma n equals 1 to infinity of negative 1 to the n minus 1 over n, the original series, converges. We used the alternating series test. We showed that in the previous section. We say, so we know that this series, the original series, is not absolutely convergent, because when we took the absolute values of the terms, we found a series that was not convergent. We say that sigma n equals 1 to infinity of negative 1 to the n minus 1 over n is conditionally convergent. So the previous example, we took the absolute value and we found that the new series converged. That's called absolutely convergent. In this case, when we took the absolute value, we did not get a converging series, so we know it's not absolutely convergent. However, the original series, without the absolute value, did converge using some other test, and when that happens, we get a conditionally convergent series. So a series, sigma a sub n, is called conditionally convergent if it is convergent but not absolutely convergent. Now, if we have an absolutely convergent series, we have a theorem associated with it. The theorem says if a series is absolutely convergent, then it is convergent. So if we can take the absolute value and find that it's a convergent series, then the original series was also convergent. Now this is a useful theorem. So this is useful for series that have terms where the signs change but not alternating. And we'll see examples of that shortly. All right, so consider the series sigma n equals 1 to infinity of cosine of 5n over 5 to the n. Now, this is not an alternating series. But we know from trigonometry that the cosine of 5n is going to be between -1 and 1, inclusive. And so what happens is, as n changes, that cosine of 5n changes, and it keeps on moving in between and including -1 and 1. But it's not necessarily alternating. So we cannot use the alternating series test. So what I'm going to do is try to see, is this absolutely convergent? So here's my question. Is it absolutely convergent? Let's check. So let's now consider sigma n equals 1 to infinity absolute of cosine of 5n over 5 to the n. All right, so now look at the terms. Let's see, absolute value of cosine of 5n over 5 to the n. Well, if we have an absolute value of a quotient, we can break that up. And so that would be the absolute value of cosine of 5n over the absolute value of 5 to the n. Now, 5 to the n, since n is, 5 to the n is always positive. And so we don't even need these absolute value bars around the 5 to the n. Now, cosine of 5n is between -1 and 1, right? Cosine of 5n is between -1 and 1. So what that means is, under absolute value, the absolute value of cosine of 5n, this numerator must be less than or equal to 1. Since the cosine of 5n moves between -1 and 1, then under absolute value, the cosine of 5n must be less than or equal to 1. And so then we can say that absolute cosine of 5n over 5 to the n is then less than or equal to 1 over 5 to the n. So what have we just done? We've taken the terms of a series, these absolute value terms, we've taken those terms and we've shown that those terms are less than or equal to 1 over 5 to the n. Now, sigma n equals 1 to infinity of 1 over 5 to the n, well, that's the same as sigma n equals 1 to infinity of 1/5 to the n, which converges. That's a geometric series with absolute r less than 1. So therefore, sigma n equals 1 to infinity of absolute value cosine 5n over 5 to the n converges by comparison. Right? We just used the comparison test. Further, sigma n equals 1 to infinity of cosine of 5n over 5 to the n is absolutely convergent and is therefore convergent. So what did we do? Let's look back. We had this original series. We wanted to, the basic question for series, is it convergent? Well, we don't know what to do with that one right away. So what we did is, I took the absolute value of the terms. Now, under absolute value, we did a little bit of manipulation. We were able to then compare it to a series that we knew converged. In fact, we were able to compare it to this geometric series. And so under absolute, the series converges. And from our theorem then, if a series is absolutely convergent, it is convergent. And so we were able to prove that the series converged by proving that it was absolutely convergent. So there's one example of how to use absolute convergence to prove convergence of a series. Now we're going to learn about a couple of tests that are very useful in determining if a series is absolutely convergent. The first of these tests is called the ratio test. And this test we're going to use frequently in a later section where we learn about a type of series called a power series. And we often use the ratio test to prove convergence, we use it when determining convergence of a power series. The ratio test says if the limit as n approaches infinity of the absolute value of the n plus first term over the nth term of the sequence is L, where L is less than 1, then the series is absolutely convergent. If, however, that limit is greater than 1 or infinite, then the series is divergent. And if the limit is exactly 1, then the ratio test is inconclusive and we have to try something else. The ratio test is particularly useful if the a sub n contains factorials and or exponentials. but it can be a very useful test in those situations. So now we're going to consider several examples of this ratio test. All right, so we're going to look at some series here, and our question is, does it converge or diverge? All right, that's our basic question with these series. All right, so consider the series sigma n equals 1 to infinity of n factorial over 100 to the n. All right, so I look at this series and I see, hey, it's got a factorial and an exponential. I'm going to try this ratio test. And recall that n factorial means 1 times 2 times 3 times 4 times ... times n minus 1 times n. Yes, n factorial. All right, so our a sub n is n factorial over 100 to the n. So if I'm going to use the ratio test, I take the limit as n approaches infinity, absolute value of a sub n plus 1 over a sub n. All right, so I know what the a sub nth term is. The a sub n plus first term would be n plus 1 factorial over 100 to the n plus 1. So I'd have the limit, n approaching infinity, absolute value. A sub n plus 1, that would be n plus 1 factorial over 100 to the n plus 1. That's all divided by a sub n, which is n factorial over 100 to the n. Enclose the absolute value. Now there's no negatives going on here, so I don't need to worry about the absolute value bars. We'll use a little bit of arithmetic here. This becomes then the limit with n approaching infinity. Let's get rid of that division by a fraction. I would have an n plus 1 factorial times 100 to the n over n factorial 100 to the n plus 1. All right, so now we have to simplify this. Limit n approaching infinity. Now, what is n plus 1 factorial? Well, n plus 1 factorial would be 1 times 2 times 3 times 4 times n plus 1. So, let's see. N plus 1 factorial, 1 times 2 times ... times n minus 1 times n plus 1. And then I have 100 to the n. In the denominator, I have 1 times 2 times ... times n minus 1 times n. And now I have 100 to the n plus first power in the denominator. Well, 100 to the n plus first power is 100 to the nth power times 100. And so notice that lots of nice things happen here. All of these factors up through the n remove, and then I have a 100 to the n that removes as well. And so then this becomes the limit with n approaching infinity of n plus 1 over 100. And as n approaches infinity, this goes to infinity. So therefore, sigma n equals 1 to infinity of n factorial over 100 to the n diverges by the ratio test. Because it met that second case. Let's look back on the previous slide. All right, the second case, if the limit of absolute a sub n plus 1 over a sub n is infinite, then the series is divergent, and that's what we just got. So again, the series diverges by the ratio test. All right, here's another example. We have n to the 10th over negative 10 to the n plus first power. And I see an exponential, right? I see that n plus first power in the denominator. That's an exponential. I'm thinking ratio test. All right, so my a sub n is n to the 10th over negative 10 to the n plus 1. And so then, if I'm going to think of the ratio test, a sub n plus 1 would be n plus 1 to the 10th over negative 10 to the n plus 1. So we're going to try the ratio test. Let's take the limit with n approaching infinity. Absolute, a sub n plus 1, that's the n plus 1 to the 10th power over negative 10. No, that denominator should be an n plus 1 plus 1. That's an n plus 2 in the a sub n plus 1. Sorry about that. Over n plus, I'm sorry, that would be an n to the 10th. All right, we're in the a sub n here in the denominator. So that would be n to the 10th over negative 10 to the n plus 1. Now, under absolute, those negative 10s just become 10s. All right, so I can write this as limit n approaching infinity. Going through the arithmetic here, I'd have an n plus 1 to the 10th. I would have a positive 10 to the n plus 1 power. In the denominator, I'd have an n to the 10th, and I'd have a 10 to the n plus 2 power. Now, if we focus on the 10s here, right, I have 10 to the n plus 1 over 10 to the n plus 2. We have one more factor of 10 in the denominator. So, limit n approaches infinity. I'd have an n plus 1 to the 10th over n to the 10th. And I'd have a 10 in the denominator. I can bring that 1/10 outside. So I've got 1/10 limit n approaching infinity. And notice that that everything left over is to the 10th power. So I can write that as n plus 1 over n to the 10th power. All right, I can simplify that fraction, n plus 1 over n. So that's 1/10 limit n approaching infinity, 1 plus 1 over n to the 10th. And as n approaches infinity, 1 over n approaches 0 as n approaches infinity, so I've got then 1 to the 10th, and so then that ends up being 1/10 times 1 to the 10th, which is 1/10. So, conclusion. Therefore, sigma n equals 1 to infinity of n to the 10th over negative 10 to the n plus 1 converges by the ratio test. Why did I say converges? Well, let's look back 2 slides. So what did we had? We had that limit ended up being 1/10, and 1/10 is less than 1. So if that limit of a sub n plus 1 over a sub n is less than 1, then the series is absolutely convergent and therefore convergent. So I really wasn't very careful here. I should have said, therefore, the series converges absolutely by the ratio test, and therefore, right, and then sigma n equals 1 to infinity of n to the 10th over negative 10 to the n plus 1 converges. Right? We know that it converges absolutely, and so it therefore converges. All right, let's consider another example here. sigma n equals 1 to infinity of negative 1 to the n minus 1 power times n over n squared plus 4. Now this is not a great candidate for the ratio test, because notice it does not involve any exponentials. It does not involve any factorials. And in fact, if you try the ratio test, and I would strongly suggest that you do this. You should try the ratio test on this and see what happens. If you try the ratio test, you should find that the limit as n approaches infinity of a sub n plus 1 over a sub n under absolute, you should find that that limit is exactly 1. Which, remember, in that slide, if you go back 3 slides, this tells us that the ratio test is inconclusive. So the ratio test tells us nothing about this series. So we are going to have to try something else, right? If you find out that, one test doesn't work, that doesn't mean you just stop, right? You have to go and then try something else. All right, so here's what I now notice. So let's look at this again. Well, I've got this negative 1 to the n minus 1. Let's try the alternating series test. And let's see what that tells us. All right, so the alternating series test, if we forget about the negative 1 to the n minus 1, if we consider n over n squared plus 4, well, that would be less than n over n squared, wouldn't it? N over n squared plus 4 is less than n over n squared, so it's decreasing. And limit as n approaches infinity of n over n squared plus 4, that would be, by L'Hopital's rule, that would be the limit as n approaches infinity of 1 over 2n, which does approach 0. So we know that sigma n equals 1 to infinity of negative 1 to the n minus 1 times n over n squared plus 4 converges by the alternating series test. Now, we know that the series converges. Does it converge absolutely? So, is it absolutely convergent? Well, let's see. So if I look at the absolute value of a sub n, that would be n over n squared plus 4. And notice that that looks similar to 1 over n, right? If you just look at the powers. So I'm going to now do a limit comparison. Let's limit compare to sigma 1 over n. And the limit as n approaches infinity of n over n squared plus 4 over 1 over n is a limit with n approaching infinity of n squared over n squared plus 4. And if you go through L'Hopital's rule, this is then equal to 1, which is not, which is equal to 1. And recall from the limit comparison test that since this is 1 and sigma 1 over n diverges, so what that tells me is sigma n equals 1 to infinity of n over n squared plus 4 diverges by limit comparison And so what that tells me is the original series by the alternating series test converges. However, it's not absolutely convergent, so a conclusion that I could make is that the original series is conditionally convergent. A second useful test in determining absolute convergence of a series is called the root test. And this is particularly useful when the series involves nth powers. And this test tells us that if the limit as n approaches infinity of the nth root of absolute a sub n is equal to L, which is less than 1, then the series sigma a sub n is absolutely convergent and therefore convergent. If the limit is greater than 1 or is infinite, then the series is divergent. If the limit is exactly 1, then the ratio test is inconclusive. So quite similar to the conditions for the ratio test. So let's see a couple of examples. So consider the series sigma n equals 1 to infinity of negative 2 to the nth power over n to the nth power. So I see these nth powers, I'm thinking, let's use the root test. So I'll take the limit, n approaching infinity, of the nth root of absolute a sub n. So that's the limit, n approaching infinity, nth root, absolute, negative 2 to the n, over n to the n. All right, now under absolute value, that the negatives go away here, so we would then have limit, n approaching infinity, nth root of 2 to the n over n to the n. All right, the nth root of 2 to the n over n to the n, that becomes then the limit with n approaching infinity of 2 over n. And as n approaches infinity, 2 over n approaches 0, which is less than 1. So, by the root test, sigma n equals 1 to infinity of negative 2 to the n over n to the n is absolutely convergent. And is therefore convergent. All right, and one more example. Consider the series sigma n equals 1 to infinity of negative 2n over n plus 1 to the 5n power. All right, so I see it's got a 5n in the exponent instead of just an n. That's okay. Let's see what happens. I'm going to try the root test. So the limit with n approaching infinity of the nth root of absolute of negative 2n over n plus 1 to the 5nth power, close the absolute. All right, so the exponential, the 5n power, that doesn't affect the absolute value. And absolute value, and vice versa, absolute value doesn't affect that. So we can bring the absolute value inside the exponent. Limit n approaches infinity, nth root of absolute of negative 2n over n plus 1, close absolute, to the 5nth power. All right, now using our rules for exponents, that nth root and the 5nth power, remember that's like saying quantity to the 5nth power to the 1 over nth power. And so if you remember your rules for exponents, you multiply those exponents, and that becomes quantity to the 5th power. So this then becomes the limit as n approaches infinity, absolute negative 2n over n plus 1 to the 5th power. Now, the absolute value n plus 1, that's not going to be affected, but that negative 2 under absolute is going to become a positive 2. So that becomes the limit then as n approaches infinity, and we would have then 2n over n plus 1 to the 5th power. Our rules for limits, which you learned back in Calculus 1, said that the limit of an expression to a power is the same as the limit of the expression then raised to the power. So what that means is I can rewrite this limit as limit n approaching infinity of 2n over n plus 1 and raise that whole thing to the 5th power. Now on the inside here, the limit as n approaches infinity of 2n over n plus 1, well, if you were to apply, L'Hopital's rule here, or whichever technique you want, you should notice that 2n over n plus 1, this, as n approaches infinity, this whole thing will now approach 2. And so then this approaches then 2 to the 5th power, which is 32. And that is greater than 1. So, by the root test, sigma n equals 1 to infinity of negative 2n over n plus 1 to the 5nth power diverges. All right, that concludes the presentation for this section.